Okay, so in particular, the curve satisfies this surface equation. Okay, and then we do implicit function theorem on it. Okay, so we get this. So you need to be a little bit alert already. You have product of sum, right? Product of sum. Linear algebra likes this. Can we split it or not? Using dot product. Okay, let's split it using dot product here. So how to split this? So we know that the left term of each product form a gradient. How about the right term of each product? What are those things? So let me write out them. So we know that these form the gradient last time. Right. Okay. So what's this dx over dt, dy over dt, dz over dt? So what are these? These are the derivative of your curve. Okay. So this is the r prime t. R prime t. Okay. Okay. So can you see that y now the gradient is orthogonal to the r prime t? The derivative of your curve. Can you see it? Why? Because from the implicit function. Okay, because it satisfies the implicit function. So you use the implicit function theorem to get the equation for your derivative. Okay. Yeah. Okay. So what's next? The next thing is normal line. Okay. So we only got the vector, right? So how to find a line? Again, finding an equation of line. So now we got the vector. So what is normal line? Okay, so I should say this is a normal line of the tangent plane. Okay, of the tangent plane. Okay, so just now we have this tangent plane made up by r prime t. Okay, actually you should ask a question. I start with a curve. Yeah, I start with a curve. Why I put a plane on that point? Any significance about this plane or not? Okay. So you can really go in different direction in your surface, right? You can consider other curve, okay? They have different direction for the tangent vector, but all the tangent vector will lie inside the tangent plane. Okay, so this is the significance of the tangent plane. And also you will see that depend on your dimension on your surface, the tangent plane have the same dimension. Okay, so for example, if it is on a one-dimensional space, you see that at one point, there's only two directions you can go. Okay, so you just get a tangent line. But for example, this sphere here is a two-dimensional surface. Okay, so you go the 2D tangent plane. So if you go to 3D, you will have 3D tangent plane. 4D got 4D tangent plane. N dimensional, you have N dimensional tangent planes. Okay. Okay. These will be proven in later course. I just give you some facts to see. Okay, so come back to this normal line business. So we know the direction of this normal line, okay, which is the gradient of f. How do I find the equation of line? Can I find the equation of line? Okay, so if you want, you can just use it now first. Okay, later we will deduce it again in chapter 3. So how to get an equation of line? So in this specific topic here, we will use the symmetric equation version of line here. Okay, so what's the symmetry equation of a line? So you will take so given ABC, a direction vector, x minus x naught over A equals to y minus y naught over B equals to z minus z naught over C is a line with direction ABC passing through S naught, Y naught, and Z naught. Okay, so I hope we will see it again in chapter 13, but I don't want to spend time deriving it now. Okay, so you just take this as your definition of line first. So how to get the equation of normal line? You just identify what point you pass through, okay, and then identify your normal vector. Okay, we already get our normal vector, which is the gradient. Okay, so to define a plane, you just need a point on the plane and a normal vector is enough to determine everything on the plane. Maybe it sounds a bit mysterious to you, but hopefully we will derive it again later. Just take my word first. Okay. Okay, let's look at some example. So for example, find the equation of the tangent plane and normal line at the point -2, 1, -3 to the ellipsoid. Okay, ellipsoid. So there's a diagram drawn here. So you got an ellipsoid. So it's a 3D version of ellipse. Like a watermelon. Okay, so where is -2, 1, and -3? Okay, at the bottom side here. So I already draw the diagram, tangent plane for you. So how to find this? Okay, how to find this? So, what's the first thing you need to have? What's the first criteria you need to have? You need to find your capital F. Okay, so what's your capital F in this case? So how to find your capital F? Your capital F have to satisfy fx, yz equals to 0. Okay. Does this looks like anything equal to 0 or not? This one equal to 3, how? This one in terms of x, y, z already. So how? Subtract 3 from both sides. Okay. This from this equation here, you will get x squared over 4 plus y squared plus z squared over 9 minus 3 equals to 0. So my capital F in this case is equals to x squared over 4 plus y squared plus z squared over 9 minus 3 equals to 0. Okay. So to get equation of tangent plane, what do you need? You need a normal vector and a point. Okay. Do you have point now? You have, right? You want to find the tangent plane at point -2, 1, -3. So what's the normal vector? Normal vector to the tangent plane. What is it? The place we start. Where is it? What's the normal vector to the tangent plane? Gradient. Okay, gradient is a vector. So you need to find gradient. So you need to find what is del f. Okay, so what's del f? Del f is fx, fy, fz, and so on, if you have more dimension. Okay, so fx is just x, sorry, x over 2, and then fy is 2y, fz is 2z over 9. Okay, so you can see that this gradient here, right, it is still a function because it still depends on x, y, z. Okay, but we want a vector on that particular point. So we need to evaluate it. So let's evaluate this gradient at -2, 1, -3. In this case, we will get -1, 2, -2 over 3. Okay. Okay, so now we have two ingredients for our plane already. So we can construct our plane. Anyone still remember what's the formula of a plane? Say ABC is the normal vector. What's the equation of a plane? A times x minus x naught plus b times y minus y naught plus c times z minus z naught equal to 0. Where s naught, y naught, z naught is a point on the plane. TikTok video. Okay. So in this case, what do we have? So we have -1 times x minus -2. Okay, yeah, right. Plus 2 times y minus 1 plus -2 over 3 times z minus -3. Okay. So in all together, if I'm not wrong, we get 3x minus 6y plus 2z plus 18 equals 0. Okay. So this is the equation of tangent plane. Follow? Okay, so far okay. Okay. So how about equation of normal line? Okay, just now what we say. What's the equation of normal line? So given a direction vector, given a point, you can make a normal line. Okay. So what's the direction for this normal line? What's the direction? Del F. Okay. So the direction of the normal line is exactly the normal vector of the tangent line. Okay. Yeah. So the general formula is x minus x naught over A equals to y minus y naught over B equals to z minus z naught over C. Okay. So altogether we get x plus 2 over -1 equals to y minus 1 over 2 equals to z plus 3 over -2 over 3. Okay. So you need to differentiate that. Okay. So now is the place where you need to think a little bit. So these two use similar ingredient, but different way to match number together. Okay. One of them give you a plane. The other give you a line. Okay. Both are using the same point, same vector. Okay. But one represent a plane, the other represent a line. Okay. What is the line? The line is the normal line. What's the plane? The plane is a tangent plane. Okay. Question? Any question now? Any question? Is it clear? Clear? So far so good. Okay. Okay, next, maximum and minimum value. Okay, so you should recall from the one-dimensional, one variable case as well. Okay, see how this generalizes. Okay, so in the surface case, we also have local maximum. Okay, we also have absolute maximum. Local maximum means if you look around that point, it is the highest. But if you look far enough, it is not the highest. Okay. So absolute maximum point is the point that is greater than any point on the surface. Okay. Similarly, you define for minimum. Okay. So what's the rigorous definition here? So we start with absolute extreme values. Probably it's easier to understand. So a point is a maximum point, or okay, so there are two things here, right? So here there are values and point. Okay, we also can call P naught as absolute maximum point. If P naught is an absolute maximum point, then F P naught is an absolute maximum value. Okay, one is a point, one is a value, domain and codomain, okay, and range. So if P naught is an absolute maximum point, sorry, leave out the maximum here, or F P naught is an absolute maximum value, then F P naught is greater or equal to FP for all P in D. Does it make sense? So FP naught is the greatest among all the value in the range of F. Make sense or not? So look at this picture here. So this is the absolute maximum because if you look at all other range, they are all lower than it. Make sense? Huh? Okay. How about minimum? Absolute minimum means it is the lowest among all. Okay, it is the smallest among all. Okay. It is the least among all. Right? Okay. If you compare to all the values in your range of F. Okay. So next thing is FP naught is an absolute extreme value if it is either an absolute maximum value or an absolute minimum value. So if it is either one, we call it absolute extreme value. Okay, either one of them. So more specifically, you can say whether it is maximum or minimum. So next part is this local extreme values. Okay, this is kind of important. Okay, so how we define FP naught is a local maximum value? If there exists a neighborhood n of P naught such that Fp naught greater or equals to Fp for all P in the intersection of D. Okay, now this part maybe sounds a bit technical, but what does it really looking at? So what is neighborhood? I think we should define this neighborhood first. Where is 时语 Where is 时语 Lost. Okay. So what's this neighborhood? Okay, what's this neighborhood? So neighborhood of P. What does it mean by neighborhood of P? Okay. So there exists an epsilon greater than 0. Okay. Uh, so there exists an epsilon greater than 0 such that, let me write down first, x minus P naught is less than epsilon. Okay. N. Okay, let me write it down properly. So N is a set. Okay, N is a set, first of all. It's a set. It's a set of what? It's a set of points in our domain, okay, such that the distance between x and P naught, okay, so this n depend on P naught, so I really should put a P naught here, okay, and there's some epsilon, so I really should fix an epsilon greater than 0. So let's fix the epsilon greater than 0 here. Okay. So there exists a neighborhood, meaning there exists an epsilon, okay? And then there are some point within epsilon with P naught. Make sense? Okay, let's look at this example here, right? So let's see how we apply this definition here. It says that Fp naught, okay, is a local maximum value if there exists a neighborhood n of P naught such that Fp naught is greater than everything inside the neighborhood can take. Bye. Bye, Sheldon. Okay, so here, the claim here is this is a local maximum. Why is it a local maximum? Can you find a neighborhood such that the value at this point is greater than any other value within the neighborhood? Can you find the neighborhood or not? Hmm? Can you find the neighborhood? Can you find the neighborhood? As long as you take a little bit greater than the neighborhood will work. Okay? A little bit away from the point. Okay, just take small epsilon. Okay, so if you take this big epsilon here, then this is not this does not satisfy the local maximum value criteria, right? Because you can find other point which is greater than this point. Okay, but remember this question, this definition just says that exists. It doesn't say for all that exists. As long as you can find it small enough neighborhood such that it is maximum for all the value, then it is a local maximum. Okay, so you don't go and pick the big one. Okay, because the big one might have other maximum point. I mean other value which is greater. So you just pick one that is small enough. Okay, because the definition is there exists. There exists means you need to find just at least one. One is enough. Okay, one is enough. So very important in mathematics is you need to show there exists or you need to show for all. Okay, there exists, you just need to pick one. As long as there's one, it works. Okay, and it turns out that this is really what we want. Okay, right? Because it is still a maximum here. Is it clear? Not clear? Yeah, sure. What's your question? Repeat definition now. Definition. Okay. So the definition of local maximum value is, okay, so there are two things here. There are P naught and FP naught. Okay, so if you take a point, you apply to F, you get a value. So this value, we say that it is a local maximum value if there exists a neighborhood of n of P naught. Okay, so you look at the point and then you look around the P naught. Okay, then you compare the value of this P with FP naught. If FP naught is greater or equal than all this FP, then we call this FP naught a local maximum value, right? FP naught. So what is the maximum value? You have to be greater or equal to everything else. Okay. So in this case, who am I comparing to? Okay. I'm comparing to the value that are in the neighborhood. Okay. I'm not comparing to everyone. I just compare to neighborhood. Okay. As long as you can find a neighborhood such that this value is greater or equal to everything in the neighborhood, then this is a local maximum value. Is it clear? Okay. Better? Okay. Okay. So similarly, you can define for local minimum. Okay. And then we will say that FP naught is a local extreme value if it is either local maximum or local minimum value. Okay. 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 Next is this extreme value theorem. I bet you already seen this in calculus 1 before. Did you? So within a closed interval, you have a continuous function, you must attain the maximum or minimum value. Yeah. So now because we go to higher dimensional, we don't have interval to talk about. So we generalize the concept of closed interval, which we call the closed and bounded set. Okay. So if f is continuous on closed and bounded set, then f attains both an absolute maximum value and an absolute minimum value then. Okay. So it is closed. What is closed and bounded mean? So example on the bottom here, we start with example first. So closed means Close means you have it is not open. Close means it's not open. So remember what's open? You still remember what's open? Seems like I need to go a little bit into topology. So what's open? What? No, what? Not close? Not close, Oh, it's okay. So, okay, open is not close, close is not open. So, I mean, you need to start somewhere, right? Okay, let's start from open. Open is easier. Okay, at least for me. So, you need to be open. Okay, be open. Yeah, be open. So, D is open if there exists, okay, so for every X in D, there exists epsilon greater than 0 such that the ball of epsilon of X is in D. Okay, so when you see this, right, don't be scared. Okay, when I talk about epsilon, right, it's just a small number. You just think of a small number. Okay, so what I mean here is if it is open, right, okay, for every point in your set, okay, I can find a ball. Ball, still remember what's the definition of ball? I think I should remind you again. So what's the definition of ball? A ball is another set. Okay. So in mathematics, right, we need to talk about what's the structure we're talking about. Well, are we talking about set? Are we talking about function? Are we talking about space? Okay, space, some space is just a set with more properties. Okay, now we're talking about set. So what's the ball means? Okay, yes, 2 days ago I mentioned it, but let's recall it. So what is a ball of radius epsilon around X? So it means that all the points that are what? So that are epsilon away from X. Okay. So you might ask me where I take this Y. Do I take Y from D or not? Okay. So really, I should say this D here, right, live in a bigger set. So let's call it universal set is what? U. Let's call it another U. Okay. So a set is open in U if for every point in your subset D there exists a epsilon such that the ball of epsilon around X is in D. Okay, it's in D. So Y is in U. Okay. Does it make sense or not? Okay. So let's see what something is open. Okay. Let's see what something is open. So this open ball is open. Okay. Open ball is open. Okay. Open in a universal set. Okay. Why? Because any point I take, right? Okay. I can take a small ball that is inside my D, such that it contains inside my D. Okay. I mean, this is strictly contained, not equal. It can be equal. I can equal, so that's fine. Okay. So I can find a ball within the point such that the ball lie inside D. Okay. Maybe you will ask, can I pick something on the boundary or not? Can I pick some? No, right? Because boundary is not inside my open ball. Okay, I don't include boundary. Okay, so this is my advantage here. Okay, so if you are open, okay, your ball is still within the set. Okay. Yeah, so your ball is still within the set. So close is not open. So you can see that this is close. Why is it close? If you think of this living in another universal set, if you pick the boundary point for any ball, you will intersect something inside and outside the set. Okay, you would never find a ball such that the whole ball is lying inside the set. Okay, make sense? Question? So what is open? Open means you are inside the set, you form the ball around you, the whole ball is within the set. that exists. So here is that exists. For every point that exists one, you just need to find one. So if you make the ball small enough, okay, you're still within the set. Okay. So you are open. Yeah, question. Right side, huh? This one. So the set that are not close, they are not close. They are not close. So why is it not close? For every ball. You mean this is not close, right? Maybe I leave out something in my definition. Let me think again. There's another definition is if it's close, it include all the limit point. So here is a closed set. Here is a not closed set. Okay, not closed. So so you think there's a problem with the definition, is it? Let me think. The close is not open. Close is not open, I think it's correct. Wait, let me think. It's a complement of a so I would say that this is open, right? So by definition, just now this is open. What's this dot? What's this line here? This is a dash line or not? Okay, this is a dash line. This is open. This is open. The open and close. Okay. So maybe I check the definition first. See if I leave out any detail in my definition, and then we will come back at 12:10. Yeah, take a break until 12:10. Is disabled. Okay. 知道我有开。
哦，OK，我现在开了一个，再试一下，再30次。
客户每一次就要24个小时啊。
没事，20小时过后才可以再交。
啊
哦，OK，不用紧嘛，反正还没有。现在第几次啊？
第二次，
第2次哦，OK。看看呢，
他会写 in progress，
什么东西 in progress？
就是如果还没有的话，会写 in progress，他不会写 fail。太完了，我帮你
看一下哦。是 this。哦，有了，有了，有了。
不是可以点进去看，但是没有在这里看到。
电子，比较别快，
没有，
反正
有吗？
滑下去，
在哪里？在哪里？在哪里？
你要滑下去，没有滑下去，滑下去，你要滑下去。
27%。
嗯，
嗯，没有啦，你要看他在查是什么东西。如果是这种什么这样子的字哦，就算了啊，又不是诊断这样，不简单，对不对？对啊
equation
，yeah,
equation
equation 吧，
equation
对
equation
一
equation
开始在讲讲，
对啊，不是 paragraph 就可以了。
哎，
不是这个
嗯，这个有什么好假的？这个，嗯，这样子。
全世界也是这样子写的。
呀，像这种 paragraph 如果是抄的，它就会出现了。
哦，这种没有中，但是很
Yeah
奇。
OK，好
对呀
了，一年，
你有数字就不会中到。
谁？
对的，他讲没有的中到手。
一年，
如果没有，没有什么没有，那时候查的话就自己手写。
不可以，不可以，要 latex。
就用那个地图打就不抄，好像东西一点不抄，还有再去做查。
反正要交到这里上面了，它自动会查。没有，你要写一些文字。
这样就行。
对，要写文字，对。对呀，
我想要付这个东西，付这推的西，然后我要下手去付。
你要等下手去 proof，
Yes，
下手去 proof。
它其实好像是polynomial series，好像是推的西是一个 polynomial series。
这是一个 power series 啊。嗯。
变成这样子的东西。
我想一下哦。这个讲说，我那时候有看到有一个article啊，书应该是有的，
都有，
书应该有吧？找看，
对对
找看啊，
对，
找看啊。
哎，
他到底要你的手。
没有 proof 啊，他们。
对，这个应该不太会有，它就丢出来给你，这样它推的系列就是这样子，然后你就套下去用了。
有proof 这个诊断啊。 theorems 你的 section 4.10已经出现过了。4.10啊。4.10。4.10。
data point。
这个你应该要证的是这个东西啊，这个东西是你要 Taylor's theorem。呀，你要这个，你要证明这整个。
OK，
这整个你要。在 Adam 的278。
那圆变成那个 open set 了，把它弄到，
要什么？
要把它变成 open set，
然后呢？
然后再怎么弄？
意思啊？我不是很懂你要做。
我要把它跟那个 open set 再重配。
重配？那什么配？怎么来的？为什么有
他的 project 是要做那 manifold 嘛，你知道
？OK， 然后你后来读了什么东西？
有那个 manifold 是讲它周围的那一个数都有一个都可以控那个RN 的 open subset。
好，
然后现在我要把它怎么样把它弄去 open subset。
他懂，
definition 写下来，写完整的 definition 下来。
他有看了 definition， 但是
对 definition 先写下来。
他不懂怎样做到。
对呀，先把 definition 写上。
摆入 project 期，因为我收集了很多那个金钱，但是发现
可以，没问题，没问题。你要不要？等一下给我看，或者你发那个Teams 给我也可以。我等一下我给你 feedback。
我已经很细。
Okay, so let's come back. Okay, so what we do just now is one place there's misconception is close and open has no connection. Okay, you can be both not open and not close. I remember, and you can be both close and open. Okay, so you can be introvert, but you still need to talk. Okay, closed and open are different. Okay, so this is an interval. Actually, I forgot this example here. So this is as I said just now, this is a generalization of interval, right? Okay, so this is what we call an open interval. I guess you already know very well. Okay, closed interval is you attain the both endpoint. Okay, this one I saw you know very well. But I think what you don't know is this one we call clopen. Both closed and open. Clopen. Okay. So this means that you can be not closed and not open, or you can be open or not closed, or you can be not open, closed, or you can be open. Cannot be open and closed, right? Yeah, cannot be open and closed. Okay. Okay, so what's wrong with the definition of closed? Actually, closed means a set is closed if it is the complement of an open set. Okay, a set is closed if it is a complement of an open set. You know what the complement of a set is? So you take your universal set, okay, and then you take out a open set, okay. To show that this is closed, I mean, to show that this is not open is true, okay, but how to show this is closed, okay? So this is closed, okay. Just now I only show that this is not open, right? Okay, because if I pick a point here, I cannot find ball that's exactly lying inside the set. But to show that this is closed, how to show this is closed? You need to show that this is a complement of an open set. Okay, so within this universe here, okay, universe set here, if I take away this closed ball, what do I left with? I left with something like this. Okay, so how about draw it somewhere else? Let's draw it somewhere else. So let's take this as my closed set and then some universal set. Okay, so I want to show that C is closed. Okay, so by definition, I need to show that we need to show C is equal to U over D for some open D. Okay, so is this C a complement of U? Some sort of complement of U. Can you find what's the open set D such that you take, after you take U slash D, you get C? Okay, so to get this right, in other words, what do you get? Actually, you get U equals to D union C. What does this mean? What union D, what union C, you get the whole thing? It's exactly anything outside, right? Okay, so is this open? So is this thing open here? Is this open? Is this complement open? For any point inside this set, can you find small enough ball that's entirely lie inside this set or not? Can you do that? Why can't? Which point doesn't work? Any point doesn't work. I mean, this universal set is anything. It's not bounded. Sorry, this thing is not bounded. This is just everything. Okay, there's no boundary here. Okay, you cannot pick point here. Nothing here. So it's anything. You get what I mean? Okay, just think of it as a universe. So if you pick any point inside this universe, right? Okay, can you find small enough ball that's lie entirely inside the set? Yes, sir. Yes or no? Means you, you look confused. Small enough. Because I just need a that exists an epsilon greater than 0. That exists. How big this epsilon, I don't care. That as long as there exists one epsilon, such that the ball is inside the set. Okay, so I just need to pick small enough to avoid I go outside the set, right? Yeah, I just pick small enough. But this small have to be positive. Okay, it's not a degenerate ball. It's a positive radius ball. Yeah, yeah. So like what I shared to you just now is the culprit is at the boundary. Okay, the culprit is at the boundary because at the boundary, right? You go to the other side, it's not in the set anymore. You go to the other side of it, it's in the set. So no matter how small the ball you pick, you still include someone outside and someone inside. Okay, so it's not good. Okay. Okay, yeah. So to show it is closed, there's some work to do. It's not just not open. Okay, not open is not open. Okay, closed is closed. Okay. So these two are closed shape. They are just a different shape. Okay. In topology, they are the same, really, because you can continuously deform it. B here is not closed. Okay, it's not closed, meaning you need to find the negation of this definition of closed. So what's the negation of this definition of closed? So if you cannot write it as a complement of an open set, okay, you cannot write it as a complement of an open set. Yeah. Okay, you cannot write it as a complement of an open set. Okay. Maybe I need you to think why you cannot write it as a complement of an open set. So if F is continuous on this closed and bounded set, then it attains both absolute maximum and absolute minimum value. Okay, so maybe we are not too rigorous, but let me tell you a bit why this closed and bounded condition is kind of important here. Okay, so you could imagine this is your domain, right? Okay, this is your domain. Okay, say this is not closed. Okay, what happened? Your function can, okay, you should imagine a z-axis coming up. Okay, can you imagine? So now we are on the domain, right? So you have a z-axis coming up. Okay, so maybe your graph grow like this, keep going up, asymptotically approaching the boundary. Remember what kind of function in one variable did this? 1 over x. Remember? Oh, let me draw it up. Let's go to the one-dimensional case. So what is 1 over x? 1 over x is like this. Okay, so you keep going up, keep going up. Okay, so if you look at the interval 0 and 1, okay, 0 and 1, this is a open, not closed. Okay, this is not closed. Okay, so this is not closed. Does it achieve maximum value or not? Within this set here? No. 100% no. You say no? No. No, right? Because it keep going up, approaching infinity. Okay, and it never reach infinity. Okay, there's no absolute maximum here. Because if you pick any ball, you will find someone that's greater than you. Okay, if you move to that point, you put a ball again, any ball, someone is greater than you. Go up, any ball greater than you again. Okay, so you cannot find an absolute maximum value. Okay, so this is why we don't like this closed, not closed set. Okay. Okay. So far, okay. Yeah. Okay. So let's keep going on. So next is how we find this upstream maximum point. Okay, how we find this upstream maximum point. So one criteria is we study the critical point. Okay, so what are the critical points? There are 3 types. One is boundary point. Second is stationary point. Third is singular point. Okay, boundary point. What's boundary point? Boundary point means the boundary of the interval. Okay, the boundary of the interval. Okay, is it clear what is the boundary of the interval is? Or the endpoint of the interval. Okay, so in 2D you also have boundary. Okay, in 2D also you have boundary. So what's the boundary of a ball? Of a 2D ball. 2D ball is what? It's a no. Okay, boundary is a circle, but 2D ball is what? It's a this, right? is a disk, 2D ball. Everything within epsilon, right, is a disk. Okay. 2D we can call it a disk. So the boundary is a circle. Okay. Yeah, boundary is a circle. A stationary point means the interior point such that the gradient is equal to 0. Right. This is what you did in your one variable calculus, right? You find the derivative and then let the derivative equal to 0, and then you do the second derivative test, whether it's greater than 0, less than 0, and then determine whether it is maximum or minimum. Okay. So this is the stationary point. Another point is the singularity point. Okay. An interior point of D where F is not differentiable. Okay. So where D is not differentiable. Okay. So where D is not differentiable, maybe it looks something like what? Something like this. Not differentiable. Okay. Perhaps not differentiable. Okay, but must be continuous, must be continuous, but maybe not differentiable. So differentiable implies continuity, but continuity doesn't imply differentiable. Okay, why is it not differentiable? Differentiable means the definition of differentiable is what? Limit. Okay, remember first principle of differentiable is limit. So if it is not differentiable, that means the limit doesn't exist. Okay, limit doesn't exist. Okay, so next is how you determine extreme value point. So if it is an extreme value, f p naught is an extreme value, then p naught must be a critical point. Okay. Yeah. So if you want to find an extreme value, that extreme value, the p naught is the critical point. Okay. Do you see the logic or not? If you want to find local maximum, absolute maximum, then P naught must be one of these critical points. Okay, either it is at the boundary, okay, it reached highest at the boundary, or stationary point, so within the interior, the gradient is 0, or the point is not differentiable within the interior. So there are two things to differentiate here. F P naught is in the range, P naught is in the domain. Okay, so value and point you need to differentiate. When we talk about point, usually it's in the domain. When we talk about value, usually it's in the range. Okay, so you need to differentiate these two. Okay, so how to find? So we need to get a strategy to find it. So since F P naught is if it is an extreme value, it must be a critical point. So we start with finding critical point. Not every critical point is an extreme value point, but extreme value point must be a critical point. Okay, so we can start by searching critical point and then check whether it is an extreme value point or not. Okay, makes sense. This is the strategy. Okay, we didn't say that once you find critical point, it must be an extreme value point. This is not the case. We find critical point first, and then we determine whether it is an extreme value point. Okay, so we like shrink down the possibility. Instead of checking every point, we just check on critical point. That's enough. Okay. So the strategy is to find the absolute maximum and minimum values of a continuous function f on a closed and bounded set. Okay, remember the 1/x example. We don't want non-closed one because maybe it should to infinity. So we find the values of stationary points. Okay. We find, so stationary points is like exactly what you do in one variable calculus. You compute gradient, let it equal 0, find a point. Okay. Next, we find the value at the singular point if there's any one. Okay. If you know that at that point it's not differentiable, and then check the value there. 3, find the extreme value on the boundary. Okay. Because at the boundary, usually the gradient is not 0. Okay, so you need to directly check whether the value at boundary is higher than the other value or not. Okay, so the largest of this value is obviously absolute maximum value, right? Because it's greater than every one of them. The smallest of these values is the absolute minimum value. Okay. So you need to check all these to determine the absolute maximum value. Okay, talk so much. So let's do one example. Okay. So let's try and find the absolute maximum and minimum value of the function x squared minus 2xy plus 2y. Okay. On the rectangle, D. Okay, so this is a rectangle. This domain is a rectangle. What's the boundary? What's the boundary of rectangle? What's the boundary of rectangle? What's the boundary of rectangle? Just the side. Okay, the side of the rectangle. So what do we want to do first? What's the strategy we say just now? What's the first thing we want to do? Similar to one variable calculus, what do we want to find first? The gradient. The gradient, we want to find the gradient first. Okay, we want to find the gradient first. So what's the gradient? So we first start with finding a stationary point. Okay. So what's the gradient in this case? The gradient in this case is x minus 2y minus 2x plus 2. Okay. So you see that one variable gradient, you only have one equation. Two variable gradient, you have two equations here. Okay, you want to set this equal to 0 vector. Okay, or set this equal to 0 vector. So you get a system of linear equation here. So when you go up dimension, right, you cannot really can't run away from linear algebra. So when you solve this, what's the stationary point here? This is x equals to 1 and y equals to 1. Okay. Before we use this strategy, right, we are using the what theorem are we using? We're using the abstract value theorem. Okay. So does abstract value theorem apply in this case? Is our f continuous or not? Is it continuous on this set or not? Is this set closed and bounded or not? Okay. So you need to check all these. Okay. Only then you can manage to find your absolute maximum or minimum value. Okay. Then the first thing you start with is to find the stationary point, just as what you did for your one variable calculus. So we already identify the stationary point, right? Okay, so what's the value at this point? F11 is just 1. Okay. Most probably, right, the stationary point you found is local maximum. Okay. Most probably. Always, I think. You can check it. It's local maximum. Okay. If it is not absolute. So then what do you do? So where is 1 minus 1, 1 here? 1 is maybe here. And then 1 is around here. So here. So you got a high point here. Okay. There's a high point here. Okay. So you still need to check if there's some more higher point at where? At the boundary or at the place is not differentiable. But in this case, is this differentiable or not? differentiable, right? Because this is just polynomial. Okay. So you just need to check boundary now. Okay. So how many boundary? So there's this, the side of your rectangle. So there are 4 lines to check here. Okay, 4 lines to check. We already labeled for you L1, L2, L3, and L4. Okay, so you need to check all these boundary line. So now we need to check boundary points. So non-differentiable point, did we give any names or not just now? Singular point. Okay. So we will say that singular point doesn't exist. Okay. The point doesn't exist. Doesn't exist. Okay. So you can see that actually this strategy, right, is kind of manual. After you found the point, you need to compute the value and then compare. So it's still manual. It is not that I check one criteria straight away give me absolute value. Okay, it's still manual. You need to compute. So you have stationary points found, singular point doesn't exist, so no need to worry about. Boundary points, we have 4 boundary to check. Okay, so what is L1? Can you represent this line or not? What's this line? This line is y equals to 0. Okay, and then you restrict it from x that is in between 0 and 3. Okay. So how does this affect my function? How does this affect my function? What happened along y equal to 0? What happened to this function? So on this point, right, y always equals 0. Okay. So I just write f(x0) is equals to x squared. Okay. S squared is a function that you know, right? So in between 0 and 3, what happened to x squared? Increase. Okay, increase from 0 to 3. So the highest point is 3. Okay, good. So the smallest point is 0, x equals 0, which is 0. And then the largest is at x equals to 3. Okay, so you can see that the whole process is manually done. Okay, we still need to compute it. How about L2? Okay, L2, what line is L2? L2 is a line that has fixed x. So it's x equal to 3. Okay, and then we go from y from where? From 0 to 2. Okay, 0 to 2. Okay. What's next? So next we need to identify what happened to the function at this line. So what is f3y? F3y is 9 minus 4y. Okay, this one even simpler. It's just a line. But what's this line behaving? How does this line behave? Decreasing. Okay, decreasing from 0 to 2. Okay, so this line decreased from 0 to 2. So meaning, where is the largest? Where do you attain the largest value here? 0. Good. So at f30, you have the largest number is 9. And then the smallest number is at 0. We should get 1, 30. Okay. So T2, sorry, at 2. Okay, 1. So you can see that when we determine this largest, smallest number for f, right, it's also manual. So if this f is some weird function, then you need to do the one variable test again, right? Okay, so yeah, okay, you get what I mean? So you reduce the case. So you reduce reduce the dimension. Okay. So L3 L3 is what? L3 is y equals to 2, okay, and then ranging from 0 to 3 for x. And then what you really get at the end for this function is just x minus 2 squared, okay. So x minus 2 squared is a shifted, this one I think a bit trickier. Is it tricky or not? This is a shifted quadratic graph, okay, shifted quadratic graph. But the range we are looking at is 0 to 3. Okay. But this graph shift to 2. So I think somewhere here. So it is 4 here. I think cut through here. Okay. So where's the largest and smallest? Huh? I think this is the right shape, right? Huh? Smallest at 2. I think there's some misleading here. It should be 9 here. Smallest is at 2. Okay. So where's the highest? 3. Okay. Can you see or not? So where's the highest? Don't mislead by this shape. You need to actually check the value. When at the other endpoint, you get 4. When at 0, you get 4, right? When x equals 0, you get 4. When x equals to, hey, yeah, I did something stupid here. Check out. No, wait. Yeah, I did something stupid here. Is it 3 or what? 1, right? Wait, let me check. Yeah, I did something stupid here. The highest point is 3. Why is it 3? Why is it 3 is the highest one? You see my graph? Okay. I mean, this graph is just sketching. So, okay. So the lowest point should be 2. Okay. Let's put the smallest one first. Yeah. 2 is 0. Okay. So where's the highest one? Is at 0, I guess. Right? 0, 2, which is 4. Okay. So you keep going. What is L4? L4 is a line from 0, 0 to 0, 2. Okay, so the x value is fixed. So it is the line x equals 0 from y from 0 to 2. Okay. So in this case here, what do we reduce to? We reduce to the graph 2y. Okay. So in this case here, I think it's relatively easier compared to what we did. So smallest one is just at a 10 at 0. X equals 0, y equals 0. And then the biggest one is attained at y equals to 2, which is 4. The value is 4 at that point. Okay? Okay. Okay, so we have all these points now. So let's check. So at 1, 1, okay, at 1, 1, we got 1. At 0, 0, we got 0. 3, 0, we got 9. 3, 1, we got 9. 3, 2, we got 1. 2, 2, we got 0. 0, 2, we got 4. 0, 0, we got 0. 0, 2, we got 4. Okay, so where are the maximum? Which one is the maximum? 9140. Yeah, 9140. 9 is the maximum. Okay, which one is the, sorry, not maximum, absolute maximum. It's absolutely maximum, not locally, absolutely. So absolute maximum. So which one is absolute minimum? The point where you get the value 0. Okay, how many points you get? 0. How many points you get 0 value? 2. One of them is, the other is, 2, 2, 2. Okay, so absolute maximum at f30, which is equals to 9. Absolute minimum at 2 point, one of them is 0, 0, the other is f22 equal to 0. Okay, so let me see if there's any helpful stuff to see here. Can you see from the diagram here about the maximum minimum? Yes, can I? So let me point out the point. So 30, where's 30? So 30, E. Why is it so weird? So 30. How should we see this? 3. Okay, so 30 is here, right? Okay, so this is a 30. 30 point is here. Okay. So you can see that this piece of cloth here is higher, right? Okay. So this point is higher. Okay. Where's the minimum one? So one of them is 0, 0. The other one is 2, 2. 2, 2, where's 2, 2? 2, 2, I think somewhere here. Right, here and here, somewhere here. Not very clear, I think, from this picture here. Yeah, but you can check. Yeah, question? Yeah.
So, determine the bound now in draw the shape.
Don't think so. No. No need to draw the shape. Just let you see what's really going on. Sometimes the shape is quite hard to draw. Yeah. No need to draw the shape. You can only determine from the algebra sense, which is what we did now. Yeah, so you need to check the stationary point, you need to check the singular point, you need to check the boundary point, and then manually compute the value, and then compare the value, and then, yeah, that's all. Okay, yeah, you cannot, sometimes it's quite hard to draw this kind of surface. Yeah, quite hard to draw. Mm-hmm. Three, right? 3 or 4? 3. So find, so you need to compute value at stationary point, compute value at singular point, compute value at boundary point, okay? And then find the largest one. Right. Okay. When you find your boundary point. What do you mean by 4 cases? Oh, the 4 cases is based on your boundary. How you split your boundary. Like, because this is a rectangle, right? You cannot do them at the same time, right? Because you can split them into lines. Okay, let's say it's a ball, it's a sphere, then you just compute the boundary. What happened to the boundary? Because I can describe the sphere just using one coordinate. Okay, I mean, I'm not quite true here, but okay. So for example, for sphere, right? Okay, let me give you another example. Okay, let me give you an example. So let's say if I want to define a function on this ball here. Okay, so this is a ball. Okay. So I want to find maximum, minimum, absolute maximum, absolute extrema here, right? Okay. So I need to determine the stationary point. Okay. Check the value. Singular point. Check the value. And the boundary point. Check the value. Okay. So what's the boundary here? Okay. Maybe this boundary looks like something x squared plus y squared equals to 1. Okay. Let's say this is my boundary. Okay. So this is my boundary. Let's say we still keep the example of our function just now, right? What's the function just now we have? X squared plus minus 2xy plus 1. Okay. So what's this boundary? Okay, so this question also can include a question is how you found the boundary, how you formulate your boundary. Okay, how you formulate your boundary. So how you formulate your boundary? So let me show this example here. Let's see if you can figure out something or not. So example. So what would I do is, similarly, I split this boundary into two parts. And then you try and figure out why do I split this boundary. And then let me know what's your problem. Okay, so I can split this into two boundaries. So one of the boundary is y equals to square root 1 minus x squared. The other is y equals to minus square root 1 minus x squared. And then I can take my s in between, my x is in between, what do we do in the polar coordinate? What do we do in the polar coordinate again? Let me think. So let's say this is actually not precise yet. So I want to take a ball centered at 0. So let me fill in all the detail here. Actually, I'm not precise, but let me fill in the detail here. Okay, so a ball with a centered 0 with radius 1. Okay, now it's very clear already. The boundary is the unique circle. So how we parameterize this guy again? So I guess the x have to run through from 0 to 1, okay? Because our x is going from 0 to 1, and then we look at all the y. Make sense? Is it true? I think it's true. I think not enough, right? 0 to 1 is just this part. So I need to go from -1 to 1 so that I get the whole thing. Okay, so I go from -1 to 1. So my x running from, okay, so behind your mind, right, you should think of this sphere here sitting on some xy plane. Not some, it's the xy plane. Okay, and then I already plot the origin. Okay, and then what is the x we are considering? We are considering x from -1 to 1. Okay, so my claim is, if I look at the x going from -1 to 1, okay, and then I follow this function here, I will get the upper circle, upper hemicircle. Do I want semicircle? Okay. So if I put negative sign, meaning I'm getting the lower semicircle, right? Because you can see that the lower part have negative value. Make sense? Okay. So now we just need to check these two. Okay. So you sub, if you want to sub f x of square root 1 minus x squared equals to something. So equal to what? Equal to x squared minus 2x times this square root function plus 2 times this square root function. And then you need to determine where's the maximum and minimum point for this function here. Within the range of -1 and 1. Okay, so now you can see that this is not quite an easy function anymore. So you need to do the one variable maximum minimum point again. Okay, so you need to compute the gradient and then check the critical point and then repeat, literally repeat the process. Okay, for the one variable case. Yeah. Oh, you mean the shape of the domain, huh? Domain. Yeah. Usually, okay, so in this class setting, right? So because our domain is 2D, I don't think we will go 3D, I guess. I don't think we will go 3D. So our domain is 2D, so 2D you still can easily do it. Yeah, sure, definitely. Yeah. For domain, you can draw it up. For the surface is quite hard to see. Yeah. Okay. Because domain still live in R2. Okay. So the question also can put triangle. How to find the line of a triangle? Equation for triangle. Triangle is some slanted x, right? So you need the gradient, equation of line, gradient. Okay, so you need to figure out what's the gradient, and then you figure out the equation of line. Because the line is not as straight as this rectangle anymore. Okay, or you can get trapezium. So two slanted, one, two straight. Okay, yeah. So depend on what you can get. Okay, you will see this in future, I guess, in the test. Oh, one second. Cannot, because it. Oh, you mean? Wait. Okay, so let me repeat your question. So you mean if the domain is not closed, should we proceed to find the absolute maximum or minimum value, right? Is this your question? Okay, this is a very good question. Actually, can be a trick question. So this is very good. Okay, that's why I give you that kind of a question in your test so that you will think like this. So the theorem says if it is closed and bounded, continuous on closed and bounded, then it attains maximum and minimum value. But it doesn't say that if it is not closed and bounded, then it cannot attain. It doesn't say this. Okay. So it could be the case that if it's not closed, it still attain the absolute maximum and minimum value. Okay. Makes sense? Okay. Okay. And yeah, very good. Yeah. This is the kind of a mindset I want you to cultivate. Yeah, question? Oh, yeah. So you need to determine what happened close to the boundary. So you need to find the limit close to the boundary. If that limit going down or if it go up, then if it go up is what we discussed just now, right? So if we go down, then it will be good because there will be someone is higher. You get what I mean? So if it's not close, but that limit go up is what we discussed just now, which is we don't want because we cannot find absolute or maximum. But just now I said that it is possible to find absolute maximum or minimum, provided the limit behave better. Okay, we don't understand well. Okay, good, very good, very good, very good. Good. Any more questions? Ah, 55 already. We still have 1-2 things to go before we go to integral. Okay, so next week we will finish up this chapter and then we will jump into integral, multiple integral. Okay? Yeah, question? Today you need to take attendance, so please come here and take your attendance before you leave. And if you are interested in your mark, you can see it also.
在我的因为在我就是一开始我跟你讲了，我要 derive Fourier transform， 我 derive Fourier transform from Fourier series 嘛。